Space, the final frontier. It's a vast expanse of mysteries, some of which we'll unravel today. Welcome to an hour-long journey through the cosmos with Sci-Sips.
Get ready, because we're diving headfirst into the mind-blowing world of space science. This is where the magic happens, where we unravel mysteries that have forever transformed and are still redefining our perception of the cosmos. From the explosive Big Bang theory to the enigmatic world of dark matter, space science is an adrenaline-fueled adventure, a celebration of human curiosity and our relentless quest for knowledge. But what good is knowledge if we can't use it to explore the great beyond? Enter space vehicles and the future of interstellar travel. We've gone from the Wright brothers' first flight to SpaceX's Mars ambitions in a little over a century. It's a testament to human ingenuity, a promise of a future where the stars are within our reach. To understand this future, we must first understand the fabric of the universe itself. This brings us to general relativity, Einstein's monumental theory that redefined our understanding of space and time. It's a mind-bending dive into black holes, gravitational waves, and the very structure of the universe. Speaking of minds, let's meet the brilliant space scientists who've dedicated their lives to decoding the cosmic conundrum. These are the men and women who stand on the shoulders of giants, their eyes firmly set on the stars, their minds a whirl of questions and theories. Now let's shift our gaze to Saturn, the jewel of our solar system. But did you know its iconic rings are disappearing? We delve into the science behind this cosmic phenomenon, shedding light on the intricate dance of ice and gravity that shapes Saturn's stunning silhouette. Next, we'll take a leap of faith with NASA's CAT video from deep space. It's a whimsical yet profound reminder of our place in the universe, a testament to our ability to find joy and wonder even in the farthest reaches of space. Time travel has always been a tantalizing concept, hasn't it? We'll journey through paradoxes and scientific possibilities, exploring the fine line between science fiction and scientific reality. Finally, we'll brave the storms from space. The ionosphere, our planet's atmospheric key, is more than just a layer of the atmosphere. It's a dynamic, ever-changing shield that protects us from the sun's fury, a testament to the delicate balance that sustains life on Earth.
So buckle up, fellow space enthusiasts. It's going to be an hour of awe-inspiring, mind-bending, and utterly fascinating journey through the cosmos.
What if our reality were but a speck in an endless sea of universes? A thought-provoking question that leads us to the intriguing idea of the multiverse theory. This theory suggests that there might exist a multitude of universes, an infinite number perhaps, each one distinct. Each one with its own set of physical laws and constants. Our universe, with its galaxies, stars, and planets, might be just one among an infinite expanse of realities, all residing in this grand cosmic ensemble. Now you might ask, what could give rise to such a bewildering array of universes? The answer lies in the concept of cosmic inflation. Cosmic inflation is a theory that attempts to explain the uniformity and flatness of our universe. It proposes that a fraction of a second after the Big Bang, the universe underwent a rapid expansion, inflating like a balloon at an exponential rate. But here's the twist. If inflation happened once, there's a good chance it could happen again and again in different regions of space. This process, known as eternal inflation, could give birth to a plethora of universes, each with its own Big Bang event, each carving out its own pocket in the cosmic quilt. This is where the multiverse theory comes into play. Each of these inflating pockets of space-time could potentially become a universe unto itself, with its own unique properties and laws. A multiverse, composed of a boundless sea of universes, each one as real as the next, and we living in just one of these myriad realities. But of course, this is all theoretical. We have yet to find concrete evidence of other universes. It's a tantalizing idea, though, isn't it? The possibility of a reality beyond our own, of worlds unexplored, of mysteries untold. As we unravel the secrets of our universe, we stumble upon more questions than answers. And in the pursuit of these answers, we venture deeper into the cosmos, into the boundless universe, and perhaps into the infinite multiverse. In the grand cosmic tapestry, what threads hold the universe together? Let's delve into this intriguing question. Our universe, vast and enigmatic, is held together by an invisible, intangible fabric known as space-time. This concept, a cornerstone of modern physics, is a four-dimensional framework, combining the three dimensions of space with the one dimension of time. Space-time isn't a mere backdrop for the cosmos to unfold upon, but a dynamic entity that bends, stretches, and warps under the influence of matter and energy. This radical notion was brought to the forefront by Albert Einstein's theory of relativity, which revolutionized our understanding of the universe. Einstein's special theory of relativity, introduced in 1905, proposed that the laws of physics are the same for all observers, regardless of their relative motion. Moreover, it suggested that the speed of light in a vacuum is constant, irrespective of the motion of the source or the observer. Then, a decade later, Einstein took a leap further with his general theory of relativity, which integrated gravity into the fabric of space-time. According to this theory, massive objects deform space-time around them, creating what we perceive as gravity. Picture a bowling ball placed on a trampoline, causing it to sag. Now, if you roll a marble along the trampoline's surface, it will spiral towards the bowling ball, not because of a mysterious force pulling it, but because the bowling ball has warped the trampoline's surface. In a similar fashion, the sun's colossal mass warps the space-time around it, causing planets like Earth to orbit. This understanding of the universe as a grand cosmic ballet choreographed by the interplay of space, time, and matter has shaped the way we study the cosmos, from the tiniest particles to the largest galaxies. It has opened doors to black holes, gravitational waves, and the Big Bang, subjects we'll touch upon later. Space and time, intertwined, set the stage for the greatest show in all existence. What mysteries lie within the smallest scales of the universe? Welcome to the quantum realm, where the rules of classical physics bow to the whimsical and paradoxical laws of quantum mechanics. This realm is so incredibly small it's nearly impossible to comprehend. We're talking about scales of a billionth of a meter. At this size, particles and waves become indistinguishable. They exist in a state of superposition, embodying both particle and wave properties simultaneously. This is quite a departure from our everyday experiences, where a thing can only be one thing at a time. The quantum realm is also home to one of the most intriguing phenomena in physics, quantum entanglement. This is when two or more particles become interconnected in such a way that the state of one instantly influences the state of the other, regardless of the distance between them. This phenomenon, famously described by Albert Einstein as spooky action at a distance, defies our understanding of space and time. It's as if these entangled particles are communicating faster than the speed of light, which, according to Einstein's theory of relativity, is the universal speed limit. Yet quantum entanglement is not just a theoretical concept, it's an experimentally confirmed fact. It's even being harnessed today to develop quantum computers and quantum encryption technologies. So, how can we make sense of this paradoxical nature of the quantum realm? Well, the truth is we're still trying to figure it out. Theories abound, from the many worlds interpretation, which posits an infinite number of parallel universes, to the pilot wave theory, suggesting that particles are guided by a wave field. What's clear, however, is that the quantum realm is a fascinating world that challenges our understanding of reality. It's a place where particles can be in two places at once, where cause and effect can happen in reverse, and where time can flow both forwards and backwards. In the quantum realm, reality as we know it takes a bizarre turn. How did it all begin? What sparked the birth of our universe? These questions have been the driving force behind the relentless pursuit of cosmologists and physicists alike. The Big Bang Theory, the most widely accepted explanation, paints a vivid picture of the universe's inception. It posits that the universe originated from an extremely dense and hot state, a singularity, around 13.8 billion years ago. It was not an explosion, but rather an unfathomable expansion of space itself that marked the beginning of time, space, and matter as we know it. The conditions that led to this birth were indeed extraordinary. The universe was a hot, dense soup of particles and energy. As it cooled, particles coalesced to form atoms and eventually stars and galaxies. However, the universe's expansion wasn't just a simple, uninterrupted process. Enter dark matter and dark energy, the enigmatic actors of our cosmic drama. They may not be visible, but their effects are undeniable. Dark matter, an elusive substance yet to be directly detected, interacts only through gravity. It binds galaxies together and forms the cosmic web, the large-scale structure of the universe. It's the unseen scaffolding on which galaxies are built. Dark energy, on the other hand, is even more mysterious. It's a form of energy that permeates all of space and is responsible for the accelerated expansion of the universe. It's like a cosmic anti-gravity pushing galaxies apart. These invisible entities play a crucial role in the universe's expansion and evolution. They are the unseen hands that shape our universe, influencing its structure and destiny. In the grand scheme of things, the birth of the universe was a symphony of cosmic forces, a delicate balance between matter, energy, and the fabric of space-time. From the fiery singularity, the universe took shape, giving birth to galaxies, stars, planets, and eventually, life as we know it. From a singularity, the universe was born, setting in motion the cosmic dance we bear witness to today. What does the Big Bang Theory tell us about our cosmic origins? In the grand tapestry of cosmos, the Big Bang Theory offers us a compelling narrative. It's a tale of an infinitesimally small singularity burgeoning into an ever-expanding universe. This theory isn't just a story spun from thin air, it's grounded in hard, empirical evidence. Among the most convincing of these evidences is the cosmic microwave background radiation. Imagine a faint echo, a whisper of the universe's fiery birth persisting through eons. That's the cosmic microwave background radiation for you. It's a relic from a time when our universe was just a cosmic toddler, barely 300,000 years old. The discovery of this radiation in the mid-20th century was a pivotal moment, providing the much-needed empirical support for the Big Bang Theory. This radiation is remarkably uniform, with minute variations that speak volumes about the initial conditions of the universe. It's akin to a baby's first photograph, providing clues about the universe's density, composition, and rate of expansion. Speaking of expansion, the Big Bang Theory doesn't just look back, it also gazes forward. The universe, it asserts, will continue to expand, driven by the mysterious dark energy. Galaxies will drift apart, stars will exhaust their nuclear fuel, and the cosmic microwave background radiation will continue to cool and fade. But what happens in the end? Will the universe keep expanding forever, becoming a cold, dark, and desolate place? Or will it eventually contract, leading to a big crunch? The Big Bang Theory doesn't provide definitive answers to these questions, leaving room for speculation and further research. The Big Bang Theory, a testament to humanity's quest for understanding, serves as our best explanation for the universe's origins. Yet it leaves us yearning for more answers in the grand cosmic puzzle. If you enjoyed that journey through space science, don't forget to like this video and subscribe to SciSips.
What if one could journey beyond the confines of our pale blue dot? What if voyages to distant galaxies become as mundane as a subway ride? Picture this for a moment, a future where space travel is not only possible but commonplace, where humanity is not confined to Earth, but spread across the cosmos. The potential for such a future is not pure science fiction. It's an eventuality that many believe is just around the corner. Imagine space cities, bustling with activity, floating in the vacuum of space. These colossal structures could be humanity's new frontier, a testament to our ingenuity and thirst for exploration. Factories too might find a new home among the stars. With abundant solar energy and a vacuum environment, space could offer unique manufacturing possibilities that are impractical or impossible on Earth. All these visions of the future hinge on one crucial factor: space travel. We're not talking about the occasional rocket launch. We're talking about regular, reliable, and efficient voyages beyond our atmosphere. For that, we need vehicles capable of handling the rigors of space travel. Vehicles that can carry us to the Moon, Mars, and beyond. From rockets that defy gravity to spaceplanes that blend the best of aviation and astronautics, the future of space travel will be defined by the vehicles we build. We'll see satellites that monitor our planet, probes that venture into the unknown, and landers that touch down on alien worlds. We'll witness the rise of space logistics, with cargo ships ferrying supplies and space tankers replenishing propellant, keeping our off-world endeavors running smoothly. And we'll marvel at the deployable structures that expand our living and working spaces in the cosmos, like inflatable modules that can be packed away for the journey and expanded once in orbit. These are the vessels that will carry us into the future. These are the tools we will use to carve out our place in the cosmos. As we stand on the precipice of this new era, one must ask, what vessels will carry us into this brave new world? The cornerstone of space travel, the rocket, has been our workhorse for decades, propelling us beyond the stratosphere and into the cosmos. Rockets, with their powerful combustion engines, harness the laws of physics, specifically Newton's third law, to thrust against Earth's gravity. They carry everything from satellites to humans into space. Yet they are not alone in this venture. Sharing the stage are space planes, an intriguing blend of aircraft and spacecraft. With their dual nature, they take off like traditional planes, but can reach the edge of space. The propulsion systems of these vehicles are a marvel of engineering. Rockets utilize chemical propulsion, burning fuel to create a high-pressure and high-temperature gas. Spaceplanes, on the other hand, employ both jet engines for atmospheric flight and rocket engines for space travel. Technological advancements continue to reshape these vehicles, improving efficiency and reducing costs. These vehicles, though rudimentary compared to what the future holds, serve as the foundation upon which we will build our celestial future. While rockets and spaceplanes ferry us to the stars, satellites, probes and landers serve as our eyes and ears, exploring the vast expanse on our behalf. These celestial scouts come in various forms, each with a unique mission. Communication satellites, for instance, are the invisible facilitators of our global connectivity, while Earth-observing satellites monitor our planet's health from above. Then we have space probes, the intrepid explorers that venture into the great unknown, capturing data and images that broaden our cosmic understanding. Probes like Voyager and New Horizons have even left our solar system, pushing the boundaries of human knowledge. Planet landers, on the other hand, are our boots on the ground, so to speak. They touch down on alien terrain, drilling, sampling and analyzing, unraveling the mysteries of distant worlds. In the future, expect even more advanced satellites, probes and landers, ones that are more autonomous, resilient and capable of exploring farther and deeper. These silent explorers traversing the cosmos are the unsung heroes of our celestial endeavors. In the inhospitable expanse of space, logistics become a monumental task. Yet we have found ways to conquer these challenges through cargo ships and space tankers. Space logistics is a field that marries the complexities of space travel with the practicalities of supply chain management. At the heart of this field we find two key players, cargo ships and space tankers. Cargo ships, much like their terrestrial counterparts, are the unsung heroes of space exploration. They ferry equipment, supplies and even personnel between Earth and various outposts in our solar system. These juggernauts are designed for long-haul voyages, equipped with advanced propulsion systems and a myriad of storage solutions to accommodate diverse cargo types. Now, let's shift our gaze to space tankers. These vessels are essentially flying fuel stations. They are designed to rendezvous with satellites and other vehicles in orbit, replenishing their propellant and extending their operational lifespan. This not only saves resources, but also reduces space debris by keeping satellites functional for longer. As we look towards the future, we see advancements in autonomous navigation and robotics playing a pivotal role in space logistics. Picture autonomous cargo ships traversing the cosmos, piloted by advanced AI, while robotic arms manipulate cargo with surgical precision. These logistical leviathans are the lifeblood of our cosmic conquests, ensuring our survival in the vast expanse. Space, while vast and awe-inspiring, is also harsh and unforgiving. To survive, we have devised deployable structures like inflatable modules. These technological marvels are designed with a specific purpose, to provide a safe and comfortable environment for astronauts during their extended stays in space. The design of these structures is a masterclass in engineering, balancing the need for robustness to withstand space's harsh conditions with the requirement for lightweight and compactness during transport. Constructed from durable, flexible materials, these modules can be packed tightly into a spacecraft and then inflated once in orbit. They offer a much-needed increase in living and working space aboard space stations. The future holds even more promise. Engineers are already conceptualizing inflatable modules that can self-assemble or are equipped with radiation shielding or can even grow their own food. These deployable structures, while seemingly simple, are critical to our survival in the harsh reality of space. As we venture deeper into the cosmos, we stand on the brink of a new era, one where space travel transcends the realm of science fiction. The future of space travel teems with possibilities that were once mere figments of imagination. The advancements in space vehicle technology are accelerating at an unprecedented pace, pushing the boundaries of what is feasible. The rockets of tomorrow will be more efficient, capable of carrying larger payloads, and will be reusable, making space travel more cost-effective. Spaceplanes will offer routine suborbital flights, turning space tourism into a viable industry. Satellites, probes, and landers will continue to serve as our eyes and ears in the cosmos, providing invaluable data about the universe. We'll see more sophisticated deployable structures such as inflatable modules, which will revolutionize the concept of space habitation, paving the way for space cities and factories. Space logistics will become a crucial aspect of our extraterrestrial endeavors. Cargo ships and space tankers will facilitate the transportation and replenishment of resources, ensuring the sustainability of our space missions. All these innovations are not mere conjecture. They are based on the progression of technology and our ever-increasing understanding of the universe. They hold the potential to transform our civilization, opening up new avenues for exploration, colonization, and resource utilization. The cosmos beckons, and with these vessels, we shall answer its call. The future of space travel is here, and it is more exciting than we could ever have imagined. Thank you for joining us on this journey through the future of space travel. It's a road filled with infinite possibilities, and we are thrilled to have you aboard, exploring it with us. If you found this video illuminating, and you're as excited about the future of space travel as we are, give us a thumbs up. It helps us reach more like-minded explorers and share knowledge about the universe we inhabit. Don't forget to share this video with your friends, family, and fellow space enthusiasts. Remember to hit the subscribe button and turn on notifications to SciSip's channel on YouTube. Stay curious, stay informed, and as always, keep sipping on knowledge. Until next time, this is SciSip signing off. Remember, the universe is ours to explore and the journey has only just begun.
Have you ever considered why the universe in all its vastness operates in such an orderly manner? Ponder on this question for a moment. The universe, with its billions of galaxies, each teeming with millions of stars, all behaving in a coordinated, predictable fashion. How is it that amidst such grand chaos there is order? This isn't a result of sheer chance, but a testament to the governing principles and laws that shape the cosmos. Ever since humans looked up at the night sky, we have sought to understand these laws, to decode the cosmic language, and that's where physics comes into play. Physics, by its very essence, is the science that unpicks the fundamental mysteries of the universe. It is a beacon that illuminates the path to comprehension, leading us towards a greater understanding of the celestial ballet. And amongst the many principles that physics has uncovered, one stands out as a cornerstone in our understanding of the universe: the concept of general relativity. Now let's take a step back and delve into the realm of the early 20th century, when a certain patent clerk named Albert Einstein challenged the very foundations of our understanding of gravity. His revolutionary theory, general relativity, proposed a radical idea that gravity is not a force transmitted across space, as Sir Isaac Newton had suggested, but a warping of space and time themselves by mass and energy. This theory offered a new perspective, painting a picture of the universe where planets and stars move along paths determined by this space-time curvature, much like a marble rolling along a warped rubber sheet. It revealed the universe as a grand stage where the cosmic dance is choreographed not by an invisible puppeteer, but by the very fabric of space-time itself. What if I were to tell you that space and time are not separate entities, but interwoven into a single continuum? This idea, seemingly plucked from the realm of science fiction, is actually one of the fundamental tenets of modern physics. Let's delve into the concept of space-time. Space-time, in layman's terms, is the four-dimensional framework that combines the three dimensions of space, length, breadth, and height, with the dimension of time. It's like a cosmic loom, weaving together the fabric of the universe. How does this relate to gravity? Enter Albert Einstein and his groundbreaking theory of general relativity. Einstein proposed that gravity is not just a force, as Sir Isaac Newton had previously suggested. Rather, it's a curvature in space-time caused by mass and energy. Think of space-time as a trampoline. If you place a heavy ball in the middle, it creates a dip or curvature. Any smaller balls rolled onto the trampoline are drawn towards the larger ball, not because of an invisible force, but because they're following the curve of the trampoline. In the context of our universe, the planets, stars, galaxies, all objects with mass, are like the heavy balls creating dips in the space-time fabric. Lighter objects such as asteroids or even light itself are drawn towards these larger masses, following the curvatures in space-time. This is what we perceive as gravity. Einstein's theory revolutionized our understanding of the universe. It provided a unified description of gravity as a geometric property of space and time, or more precisely, space-time. It painted a picture of a universe not governed by invisible forces, but by the elegant warping and curving of the space-time fabric itself. So, in essence, the apple does not fall far from the tree, not because of an invisible force, but because it is following the curvature of space-time around it. This understanding of gravity and space-time is one of the most profound shifts in scientific thought, forever changing how we perceive our universe. Now let's delve deeper into how mass and energy distort space-time. First, let's introduce the metric tensor, a crucial tool. It's used to measure distances and angles in a curved space. It's a bit like a map of space-time, telling us how distances and directions change as we move from point to point. But unlike a regular map, it also includes time. Now imagine we're trying to predict the path of a planet moving in this curved space-time. To do this, we use something called Christoffel symbols. These are mathematical constructs that help us understand how space-time is bending and twisting around the planet. They're a bit like signposts, pointing the way for the planet as it travels through space-time. But how do we know how space-time itself is shaped? That's where Einstein's field equations come in. These are a set of 10 interrelated differential equations that describe the fundamental interaction of gravitation as a result of space-time being curved by mass and energy. They're the master artists, sketching out the shape of space-time in response to the presence of matter and energy. The beauty of these equations is that they're dynamic. They don't just describe a static universe, but a universe that's constantly changing and evolving. They tell us that mass and energy don't just sit there, they shape the space-time around them. And in turn, the shape of space-time tells mass and energy how to move. So if you were to take a massive star and place it in space-time, it would cause the space-time around it to curve. And if you were to take a planet and send it hurtling through this curved space-time, it would follow a path dictated by the curvature. It's a beautifully elegant system where everything influences everything else. It's like a cosmic dance, where each dancer is both leading and following at the same time. In the world of general relativity, mass and energy are the artists, and space-time is their canvas. So, what does this curvature of space-time mean for us and the universe we inhabit? As we delve deeper into the implications of general relativity, we encounter phenomena that seem to bend our perception of reality. One such phenomenon is time dilation, a concept that posits time as a variable entity, slowing down in the presence of strong gravitational fields. This is not merely theoretical. Experiments involving precision clocks flown in airplanes have confirmed this prediction, with the clocks in motion showing a slight lag compared to their stationary counterparts. Then we have gravitational waves, ripples in space-time caused by the acceleration of massive objects. These waves were first detected in 2016 by the LIGO and Virgo collaborations, providing the first direct evidence of their existence. Think of them as the cosmic whispers of the universe, echoing from the depths of space-time, carrying with them information about their cataclysmic origins. And of course, we cannot forget the enigmatic black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. These astronomical anomalies are predicted by general relativity, and their existence has been confirmed by numerous observations, most notably the groundbreaking image of a black hole's event horizon captured by the Event Horizon Telescope in 2019. These phenomena are not just abstract concepts confined to the realm of theoretical physics. They have real, tangible effects on the universe we inhabit. GPS systems, for example, have to account for time dilation effects to maintain their accuracy. Observations of gravitational waves open up a new way to observe and understand the universe, while the study of black holes continues to challenge and expand our understanding of the nature of space-time. From the ticking of your watch to the spiraling of galaxies, general relativity is at play. The universe, in all its complexity and wonder, is governed by the principles of general relativity, etching its effects into the very fabric of space-time. As we stand on the shoulders of giants like Einstein, what does the future hold for our understanding of the universe? The road to unveiling the universe's deepest secrets is still under construction. Researchers around the world are tirelessly working to answer the enigmas that general relativity poses. Some of these unanswered questions include the nature of dark matter and dark energy, the singularity at the heart of a black hole, and the earliest moments of the universe. One of the most significant pursuits in theoretical physics is the search for a theory of everything, a framework that unifies general relativity with quantum mechanics. This unification, often referred to as quantum gravity, is a holy grail of sorts. It aims to reconcile the macroscopic world of gravity with the microscopic world of quantum particles, two realms currently described by seemingly disparate theories. The completion of such a theory would be a monumental leap in our understanding of the universe. To achieve this, some physicists are diving into the realm of string theory, a theoretical framework in which the point-like particles of quantum physics are replaced by one-dimensional objects called strings. Others are exploring loop quantum gravity, a theory that quantizes space-time itself. The importance of these endeavors goes beyond mere intellectual curiosity. A deeper understanding of gravity could have profound implications for technology and practical applications. Just as Einstein's theory of relativity paved the way for GPS technology, tomorrow's breakthroughs in gravity could lead to technologies we can barely imagine today. In the grand scheme of things, general relativity is still a young theory, and we are merely at the beginning of our cosmic journey. As we venture into the uncharted territories of the universe, we shall inevitably encounter new mysteries, phenomena, and possibly even new laws of physics. As we continue to unravel the mysteries of the universe, one thing is certain: general relativity will remain a cornerstone of our cosmic understanding. Don't forget to like this video and subscribe to SciSips. Do you ponder upon the astounding complexity of the cosmos? Who are the intellectual gladiators unraveling the mysteries of the universe? Unveiling the universe is a colossal endeavor, one that requires the harmonious interplay of multiple disciplines. Welcome to the grand arena of space science, a field so vast it's divided into various branches, each contributing unique insights into our understanding of celestial bodies and phenomena. Physics, the very language of the cosmos, lays the groundwork, providing us with the principles of matter, energy, time, and space. Chemistry, on the other hand, delves into the elemental composition and reactions within celestial bodies in interstellar space. Meanwhile, mathematics serves as the universal translator, converting physical and chemical observations into comprehensible laws and models. Yet space science is not merely about equations and measurements. It thrives on two key perspectives: the observational, focusing on the empirical gathering of data, and the theoretical, dedicated to the interpretation and prediction of cosmic phenomena. Consider the observational astronomers, the eagle-eyed sentinels of the cosmos. With a telescope as their sword and detectors as their shield, they delve into the vast, uncharted territories of the universe, collecting precious data about celestial entities. These space watchers decode light spectra, unveiling the hidden secrets of far-off stars and galaxies. They measure cosmic distances, mapping the universe with remarkable precision. By analyzing the physical properties of celestial bodies, they uncover the nature of these distant objects, revealing their age, composition, and even their life cycle. Yet their work extends beyond mere data collection. The observations they make, the patterns they discern, they all pave the way for groundbreaking theories and models. Observational astronomers thus provide the raw data, the cornerstone of our cosmic understanding. Now step into the realm of theoretical astrophysicists, the master weavers of cosmic tapestry. Theoretical astrophysics is akin to a grand cosmic detective story. These scientists use mathematical models and computer simulations to decode the mysteries of the universe. They're the architects of the abstract, crafting theories that explain phenomena observed by their observational counterparts. Consider stellar dynamics, a field that explores the gravitational interactions within star clusters and galaxies. Theoretical astrophysicists predict the dance of stars, using complex equations to unlock the secrets of cosmic choreography. Then there's the cosmic microwave background radiation, the afterglow of the Big Bang. Our theorists analyze this radiation to understand the universe's infancy, unraveling its earliest moments. And let's not forget the enigma that is black holes. Theoretical astrophysicists delve into the physics of these cosmic behemoths, their work providing insights into the fabric of space-time itself. Through their work, they not only explain what we see today, but predict future cosmic events and phenomena. Lastly, meet the cosmic chemists, the alchemists decoding the universe's elemental secrets. These astrochemists are the detectives of the cosmos, unraveling the complex chemical interactions that occur in the vast expanse of space. They dive deep into the interstellar medium, the space between the stars, studying its composition to understand the birth, life, and death of molecules in the cosmos. Their work doesn't stop there. They also examine the creation of molecules in the harsh conditions of space, deciphering how the universe's vast molecular diversity came to be. Their research often leads them to investigate the origins of life's essential elements like carbon, nitrogen, and oxygen, and their cosmic journeys. But perhaps their most intriguing pursuit is the search for extraterrestrial life. By studying the chemical signatures in distant planets and galaxies, they aim to detect signs of life beyond our own blue planet. Such is the grand symphony of space science, a harmonious interplay of various scientific disciplines. The observational astronomers, our cosmic cartographers, chart the heavens, providing us with the raw data and celestial blueprints. Their work forms the foundation upon which the theoretical astrophysicists build their cosmic edifices, their mathematical models and theories offering a framework for understanding the universe's enigmatic behavior. Our cosmic chemists, meanwhile, delve into the elemental aspects, exploring the universe's molecular makeup and the cosmic reactions that fuel star systems and galaxies. A confluence of these disciplines, their collective effort propels us further into the vast cosmic ocean. As we continue our cosmic voyage, don't forget to like this video and subscribe to SciSips.
The cosmos, a boundless expanse, a swirling dance of stars, galaxies and celestial bodies. It is a testament to the grandeur of existence itself, a realm so vast it eludes the grasp of human comprehension, a spectacle of mystery and majesty that never ceases to captivate. Amidst this cosmic tapestry exists a unique ensemble of planets, each with their own intriguing tales. One such celestial body, the sixth from the Sun, is the gas giant Saturn, known for its distinct feature, a dazzling array of rings. Saturn continues to enchant observers and scientists alike. In this celestial ballet, one performer stands out with its majestic rings, the planet Saturn. Saturn, the sixth planet from the Sun and the second largest in our solar system, is a gas giant primarily composed of hydrogen and helium. This celestial body isn't just known for its colossal size, but also for its most distinguishing feature, the rings. These rings are a spectacle to behold, composed of countless small particles, most of which are ice. They're like a grand cosmic ballet, with each particle dancing in independent orbits around Saturn. Yet these rings are not a solitary act. Saturn is accompanied by a retinue of at least 145 moons, each playing its part in the cosmic dance. One moon in particular, Titan, is noted for its substantial atmosphere. These moons cast a significant influence on the rings, giving them their unique structure and appearance. Despite their width, these rings are incredibly thin, almost like a cosmic razor's edge, and even though they appear solid from afar, they consist of particles in independent orbits around Saturn. This delicate balance of ice and space dust is a testament to the complexities and wonders of our universe. In a surprising turn of celestial events, Saturn's rings, a symbol of its identity, are gradually disintegrating. This iconic symbol of the cosmos, first observed by Galileo Galilei in the early 17th century, is forecasted to undergo an extraordinary transformation. Come 2025, these magnificent rings will align edge-on with our home planet, becoming virtually invisible to the naked eye. A celestial spectacle indeed, but fret not, for this is but a temporary phenomenon in the grand scheme of cosmic time. As Saturn continues its celestial dance around the Sun, it will tilt again. And in the year 2032, the rings we've come to admire will re-emerge, revealing themselves once again in their full icy splendor. This upcoming vanishing act serves as a stark reminder of the ever-evolving nature of our universe. As we anticipate this cosmic vanishing act, we are reminded of the ever-evolving nature of our universe. As we marvel at Saturn's rings, set to disappear and reappear in a cosmic dance of celestial mechanics, we are reminded of our place in the universe. Our existence in the face of the cosmos's grandeur can seem insignificant. We are but momentary occupants of a tiny blue dot, lost amongst the astronomical spectacle of galaxies, stars, and celestial bodies like Saturn. Yet it is our curiosity, our desire to understand and explore these celestial wonders that make us significant. In the grand scheme of the cosmos, we are but a fleeting moment, a transient speck on the cosmic canvas, dwarfed by the majesty of planets like Saturn and the incomprehensible vastness of the Milky Way. If you're as captivated by this discovery as we are, and you want to dive deeper into the fascinating world of science, then we have a simple call to action for you. Hit that like button and subscribe to our channel, SciSips. We're constantly exploring and breaking down complex scientific phenomena into digestible content.
Did you even think it was possible to transmit a high-definition video from deep space? Well, the minds at NASA did, and they turned this thought into a reality. On the memorable date of December 11th, 2023, the Deep Space Optical Communications Team, or DSOC, stationed at NASA's Jet Propulsion Laboratory, achieved a significant milestone. They successfully received the first high-definition streaming video sent via laser from the depths of space. Not just any video, but one featuring a delightful feline named Taters. This video was transmitted from the DSOC transceiver aboard the Psyche spacecraft, which, at that time, was nearly 19 million miles away from our home planet. Just imagine, a video traveling through the vast expanse of space all the way to us. That's not a feat you hear of every day. The video signal took a little over a minute and a half, 101 seconds to be precise, to reach Earth. The transmission occurred at a maximum bit rate of 267 megabits per second. That's a hefty amount of data traveling at lightning speed across the cosmic highway. The DSOC technology demonstration aims to transmit data from deep space at rates 10 to 100 times greater than our current radio frequency systems. With this successful transmission, a new path has been paved for future high-bandwidth communication during interplanetary missions. In summary, the DSOC team at NASA's Jet Propulsion Laboratory has successfully received a high-definition video from deep space for the first time. The video, featuring the adorable Taters, was transmitted from the Psyche spacecraft nearly 19 million miles away from Earth. This achievement opens up new possibilities for data transmission from deep space, potentially at rates far exceeding our current systems. And don't forget to subscribe to SciSips for more intriguing insights into the world of science and technology. Until next time, keep your curiosity piqued and your minds open to the wonders of the cosmos.
Have you ever pondered the repercussions of going back in time and accidentally erasing your existence? Now that's a question to stir the gray matter, isn't it? Let's dive into the belly of the beast known as the grandfather paradox. Imagine this. You've built a time machine, you decide to test it out, you set the dial to, let's say, 70 years ago. You pop out in the past and there's your young, sprightly grandfather, oblivious to the fact that his future grandchild is standing right before him. But here's where things get tricky. You, for some unfathomable reason, decide to alter the timeline. You off your grandfather. Grim, I know, but stick with me. So your grandfather is gone long before your parents were even a twinkle in his eye. This means your parents were never born. Consequently, you were never born. But if you were never born, then who traveled back in time to eliminate dear old granddad? Thus, we find ourselves in the clutches of the grandfather paradox, a logical dilemma that has become a staple in the realm of time travel. This paradox is a compelling argument against the possibility of time travel. It's a logical loop that defies our understanding of causality and continuity. Quite a conundrum, isn't it? But hold on to your hats because we've only just scratched the surface. What if your actions in the past were not only unavoidable but necessary for your present existence? Welcome to the predestination paradox, a mind-bending concept that will have you questioning the very nature of free will. Picture this. You invent a time machine and decide to travel back in time. You meet a stranger who inspires you to become an inventor. Years later, you realize that stranger was you. You've become the very inspiration that led you to your present existence. This is the essence of the predestination paradox, a loop with no clear beginning or end. Now you might be thinking, this sounds like something out of a science fiction novel. And well, you wouldn't be wrong. The world of pop culture has given us some fantastic examples of the predestination paradox. One that might tickle your fancy is Harry Potter and the Prisoner of Azkaban. Remember when Harry conjures a Patronus to save himself and Sirius Black from the Dementors? Later he realizes that he was the one who conjured the Patronus in the first place. A classic predestination paradox. In the end, the predestination paradox presents a fascinating question. Are we truly masters of our fate, or are we simply prisoners of our own actions, trapped in a loop of our own making? It's a question that continues to baffle even the brightest minds. So we are prisoners of our own actions, trapped in a loop of our own making. What happens when an object or information has no discernible origin? Enter the bootstrap paradox, a time-twisting quandary that traps objects or information in an infinite cause-effect loop. Imagine for a moment a book. This is no ordinary book, but a tome of knowledge sent back in time. The author in the future scribes it using an older version as a reference. So the question is, who wrote the book originally, the author or the book itself? A similar scenario occurs in popular culture, specifically in the British sci-fi series Doctor Who. Remember the episode Blink? A transcript of a conversation is sent back in time and the Doctor reads from it in the present. But the transcript only exists because it was read out in the first place. This is a classic example of the bootstrap paradox. So where does this leave us? Well, in a bit of a pickle, to be honest. The bootstrap paradox is a veritable chicken and egg scenario, but with a temporal twist. It's a headache-inducing puzzle that leaves us questioning the very nature of causality and origin. Yet isn't it fascinating? It's like a never-ending waltz, where the dancers are time and matter, locked in an eternal sequence of steps without a clear beginning or end. A timeless conundrum indeed. But as they say, time waits for no one. Can you imagine a universe where time isn't linear? Now that's a head-scratcher, isn't it? Welcome to the realm of closed time-like curves, a concept that would make even H.G. Wells' head spin. In the world of theoretical physics, we're often asked to suspend our belief in the ordinary. Closed time-like curves, or CTCs, are no exception. These are solutions to Einstein's field equations in his general theory of relativity that allow for time travel. Yes, you heard it right, time travel. Here's the gist. CTCs are paths through space-time that, if traversed, could take you back to the exact moment you started your journey. It's like going on a cosmic merry-go-round where every ride takes you back to square one, no matter how far you've gone. Now, if you're picturing Doctor Who's TARDIS or the DeLorean from Back to the Future, hold your horses. The existence of CTCs doesn't necessarily mean we can start packing for a trip to the Jurassic era or the distant future. CTCs are still purely theoretical, and the universe might have safety measures to prevent such time-bending shenanigans. But isn't it fascinating to ponder the possibilities? Time travel has been a staple of science fiction for centuries, and CTCs bring us one step closer to understanding how it might actually work. Who knew physics could take us on such a wild ride? Whether it's through a wormhole, a DeLorean, or a closed time-like curve, the journey through time is sure to be a thrilling adventure. What if every decision you made spawned an entirely new universe? Now that's a question to make your head spin, isn't it? This is the heart of the many worlds interpretation of quantum mechanics, a theory that suggests all possible alternate histories and futures are not just figments of our imagination, but are as real as the universe we inhabit. Let's break it down. Imagine you're at a cafe deciding between a cappuccino and an espresso. According to the many worlds interpretation, the moment you make your choice, the universe splits in two. In one universe, you're relishing that cappuccino, and in another, you're sipping an espresso. This interpretation was first proposed by physicist Hugh Everett in the mid-20th century, and it's been stirring debates ever since. It's like a cosmic game of what if that never ends. It's a concept so vast, so mind-boggling, it's been a favorite among science fiction writers and filmmakers. Ever seen the movie Back to the Future? Well, imagine Marty McFly's actions creating not just one, but an infinite number of timelines. Or take the Avengers Endgame. Every snap of the Infinity Gauntlet, every choice made by our heroes could be spawning countless new universes. It's a lot to take in, isn't it? But we're just getting started. Could the laws of physics actually prevent time travel? It's a question that's been posed by many a curious mind. The chronology protection conjecture, a hypothesis proposed by none other than Stephen Hawking, tackles this very issue. Hawking, the renowned physicist and cosmologist, suggested that the laws of physics might actually forbid time travel to prevent any possible paradoxes. Imagine that. The universe, in its infinite wisdom, may have set up safeguards to stop us from mucking about with the delicate fabric of space-time. The chronology protection conjecture hinges on quantum physics and how it interacts with the concept of time travel. According to Hawking, any time machine would generate a massive amount of energy, enough to destroy itself before any actual time travel could occur. Now you might be thinking, well, that's a bit of a downer. But hold on to your TARDIS, because there's still hope. This is, after all, a conjecture, an educated guess, not a proven law. The physics community remains divided on this issue. Some agree with Hawking's view, while others believe there's still a chance we might find a loophole in the laws of physics. So what's the bottom line here? Well, if the chronology protection conjecture holds true, we might have to toss our dreams of time-hopping adventures into the bin. But if it doesn't, who knows what incredible journeys await us in the future? Or should I say, in the past? Perhaps time is more resilient than we thought. Could the universe be self-correcting, preventing paradoxes from occurring? Now let's delve into the Novikov self-consistency principle, the fascinating hypothesis that puts forth the idea that the timeline is inherently self-consistent and makes paradoxes an impossibility. Imagine, if you will, a time traveler journeying back into the past with the intent to alter a significant event. According to the Novikov principle, no matter how hard they try, they simply can't succeed. Why, you ask? Well, the principle posits that any event that could cause a paradox has a zero probability of happening. It's a bit like trying to break the speed of light. Physics just says no. In effect, the Novikov principle suggests that the universe has a built-in paradox prevention system. If you've ever wondered why Marty McFly's meddling in Back to the Future didn't rip apart the fabric of space-time, this principle might just be your answer. So let's say you're a time traveler and you decide to pull a Terminator and take out your own grandfather. According to Novikov, you'd be thwarted by the cosmos itself. Perhaps you'd miss every shot. Or maybe your gun would jam. In any case, the universe would conspire to maintain its own consistency. The Novikov self-consistency principle is a fascinating idea that could provide a solution to the time travel paradoxes that have puzzled scientists and sci-fi fans alike. It suggests that the universe, in all its vastness and complexity, has its own checks and balances. So, even if we could time travel, the universe has its own fail-safes. Intriguing, isn't it? How has popular culture tackled the brain-bending concept of time travel? Let's dive into the world of fiction, where time travel has been a captivating theme for decades. Consider the Back to the Future series. Here, the protagonist Marty McFly accidentally alters his parents' past, nearly erasing his own existence. This is a prime example of the grandfather paradox, where changing events in the past leads to impossibilities in the present. Then there's Star Trek, a franchise that has navigated the space-time continuum with finesse. Its many episodes have explored the predestination paradox, where characters are caught in time loops, their actions in the past ensuring the future they know. Doctor Who, the British sci-fi classic, often grapples with the bootstrap paradox. The Doctor himself explains it as an object or piece of information sent back in time becoming trapped within an infinite cause-effect loop, in which the item no longer has a discernible point of origin. And let's not forget Harry Potter and the Prisoner of Azkaban, where the use of a time turner aligns with the Novikov self-consistency principle. The principle suggests that if an event could cause a paradox, the probability of that event is zero. So while these stories may seem far-fetched, they are grounded in real theoretical concepts, making them not only entertaining but also intellectually stimulating. And we thought our reality was complicated. What does the future hold for the study of time travel? Peering into the crystal ball of scientific curiosity, the future of time travel research shimmers with possibility. quantum mechanics, that enigmatic branch of physics, is at the forefront of this exploration. As we delve into the subatomic world, we stumble upon quantum entanglement, a phenomenon that might just be the key to unlocking the secrets of time travel. Imagine, if you will, a pair of entangled particles. Despite being separated by vast distances, a change in one particle instantly affects its twin. Could this instantaneous communication be a form of time travel at a quantum level? Only time and rigorous research will tell. Then there's the field of particle physics, where researchers are investigating tachyons, theoretical particles that move faster than light. If these elusive particles exist and can be harnessed, they could potentially enable us to send information back in time. And let's not forget the role of quantum computing, a technology that could simulate time travel scenarios with unprecedented accuracy. By running complex models and simulations, these supercomputers might provide us with a deeper understanding of temporal mechanics. As we step into the future, the study of time travel continues to push the boundaries of our understanding, bringing us one step closer to answering the question, can we truly master time? The future, it seems, is full of possibilities. Should we even tamper with time if given the chance? This is where we tread into the realm of ethics, a dimension as complex and convoluted as time itself. Time travel, in theory, is a Pandora's box of endless possibilities and potential misuses. Imagine, if you will, a future where time travel is as commonplace as catching a bus. Could we trust every Tom, Dick, and Harry with the ability to alter the course of history? A single misplaced step in the past could potentially bring about the butterfly effect, leading to unforeseen and possibly catastrophic changes in the present. And then, there's the question of moral responsibility. If one could travel back in time and prevent a tragedy, would they be obliged to do so, or would doing so infringe upon the natural flow of time, causing more harm than good? Consider the Time Lord's dilemma in Doctor Who, where he must often choose between interfering and letting history take its course. Or the lessons from the Time Turner in Harry Potter, where even the most well-intentioned alterations can have unintended consequences. These ethical quandaries remind us that time travel isn't just about the mechanics or the paradoxes, it's about the profound responsibility that comes with wielding such power. Perhaps the most important question isn't how to time travel, but whether we should. Because, as Uncle Ben once told Peter Parker, with great power comes great responsibility. And in the case of time travel, the power and the responsibility could not be greater.
Have you ever pondered how invisible tempests raging miles above our heads could affect our daily lives? Welcome to the enigmatic world of geomagnetic storms. These invisible yet powerful phenomena have the potential to disrupt power grids, impair radio signals, and cause havoc with GPS systems. They are silent, unseen, yet hold the power to change our daily lives dramatically. A recent study led by the brilliant minds at Nagoya University and the University of New Hampshire has shed new light on these storms. The researchers delved into the Earth's upper atmosphere, a realm often overlooked, revealing its critical role in the development of these storms. The focus of this investigation was the magnetotail, a part of Earth's magnetosphere. In a surprising twist, the researchers discovered that during a significant geomagnetic storm, the plasma in the magnetosphere was primarily sourced from Earth's ionosphere, not the solar wind as previously thought. This revelation underscores the Earth's ionospheric plasma's role in driving these storms. Just as we thought we had the mysteries of these storms figured out, a new discovery turns our understanding on its head. And so, we continue our journey, venturing further into the storm, eager to unravel the mysteries that lie within. Imagine a world where our own atmosphere plays a pivotal role in shaping the very storms that threaten our technology. In the grand cosmic drama unfolding above us, our humble Earth has a more significant role than we ever imagined. A recent study led by a team of astute researchers has unveiled a surprising truth. Our Earth's upper atmosphere, the ionosphere to be precise, is a major influencer in the creation of geomagnetic storms. These storms, as you might know, can wreak havoc on our modern technology, disrupting power grids, radio signals and GPS. But where does the raw material for these storms come from? The answer until recently was thought to be the solar wind, the stream of charged particles emanating from the sun. However, this new study presents a different narrative. The researchers meticulously analyzed data from a large geomagnetic storm that occurred in September 2017. The protagonist of this story turned out to be the magnetotail, a part of the Earth's magnetosphere. The plot twist? They found that the plasma in the magnetosphere, the very lifeblood of the storm, was mostly sourced from the Earth's ionosphere, not the solar wind. This discovery has a profound implication. It shifts our understanding of geomagnetic storms and their development. It paints a picture of the Earth not merely as a passive spectator in the cosmic play, but as an active participant, contributing its own elements to the stormy drama. Just think about it for a moment. The very air that we breathe, the sky that we look up to, is involved in a celestial tug of war, shaping the storms that dance above our heads. It's a testament to the interconnectedness of our universe, where every player, no matter how small, has a part to play. Our very own atmosphere, it seems, is a major player in the theatre of these celestial storms. So why should we care about these invisible storms and our atmosphere's role in them? Well, think of this. Our world is increasingly dependent on technology, from satellite communications to power grids. These technological marvels, while robust, are not impervious to the effects of geomagnetic storms. With a deeper understanding of the Earth's upper atmosphere and its role in these storms, we can better predict and prepare for potential disruptions. This knowledge is not just crucial for our day-to-day lives, but also for the brave souls venturing into space. As we continue to explore the cosmos, these invisible storms remind us that sometimes the answers to our questions lie closer to home than we might think. If you're as captivated by this discovery as we are, and you want to dive deeper into the fascinating world of science, then we have a simple call to action for you. Hit that like button and subscribe to our channel, SciSips. We're constantly exploring and breaking down complex scientific phenomena into digestible content.